Welcome to our virtual presentation on Pac-Euglena for CHI 2020. My name is Amy Lamb, and I'll be talking about our new biology-based mixed reality game, Pac-Euglena. First, I'll play a short video to give you a basic overview of the game. In Pac-Euglena, the player steers real living Euglena cells, which you see moving around here, around a microfluidic maze to collect virtual Pac dots. Euglena cells are light sensitive, so we can steer them around using light. We use computer vision to track the cells, which enables them to interact with the virtual objects, like the Pac dots, and also trigger interactions with the ghost. When a Euglena cell runs into a ghost, the virtual ghost is transformed into a real-life local light stimulus, which causes the Euglena to spin in place, temporarily disabling the cell. We'll discuss some details of the iterative design process and the user study we conducted on Pac-Euglena, and conclude with some general design rules for biology-based games. Due to recent technological advances in computers and biotechnology, a whole host of human biology interactions are now possible and are starting to be explored. It's a new and exciting frontier in HCI. Historically, video games pushed the boundaries of consumer electronics and led to innovations in both hardware and software. We believe that similarly, developing biology-based games, also called biotic games, might also lead to the development of more consumer biotechnology and biotech innovation. Games are also great at building interest in technology from a young age and fostering education, which is especially important now as biotechnology becomes more relevant to day-to-day life. As you might expect, given the name Pac-Euglena, the organisms we feature in this game are Euglena gracilis cells. Euglena gracilis is a unicellular organism that moves in response to light stimuli, tending to move away from bright lights. Euglena are really great for biotic games. They're small, being about 50 to 100 microns long, which means that setups for housing, stimulating, and observing them don't need to be all that large. Euglena cells are also easy to take care of, requiring only access to light and air. They photosynthesize, so they make their own food, and we don't have to supply them with anything extra. They can also be kept for months at a time in the same test tube. They're also nice to use because their response to light happens within 1 second. This means they're easy to interact with since they operate on a timescale that we, as humans, can observe and appreciate. Because of all of these nice characteristics, they've actually already been used in other biotic setups, as seen in CHI 2015's Trapit system. So we know that the technology needed to bridge the scale between us and the Euglena cells, which are on the order of 10,000 times smaller than us, has already been developed. We actually use one of these previously developed setups to build our game. In this setup, the Euglena cells are held inside a microfluidic chip and are viewed through a webcam on a computer screen. On each of the 4 sides of the microfluidic chip, there's an LED. These LEDs provide directional light so that the user can steer the Euglena up, down, left, and right. The chip is also lit from below by a projector, which allows us to use local light stimuli. Extra cells are held in test tube reservoirs. On the right, you see what the physical setup actually looks like. To recap, these are the stimuli and responses we have to work with. We can change the microfluidic chip so that there are different physical barriers or mazes for the cells to move around in. These barriers are made of PDMS, so they're solid, and if a cell swims into a barrier, it will have to change directions. We can turn the LEDs on or off. Cells tend to swim away from any LED that's on. Since the LEDs are placed on the sides of the chip, this provides a directional stimulus, which leads to directional swimming. We can also use the projector to project images onto the sample plane, which gives local light stimuli. Since the cells are repulsed by bright light, they tend to treat the light as a barrier. You can see the 2 types of light stimuli working together here. An LED on the bottom of the screen is turned on, forcing the cells to swim upwards away from that light. They are trapped by the projected light, though, which causes them to concentrate into the box. If the Euglena detects a very bright light, brighter than 3000 lux, it will start spinning in place, as seen here. Our goal in creating this game was to explore some open questions regarding biotic game design. Some of these questions were technical. For example, what are the design constraints on using microfluidic chips as mazes for Euglena cells? Also, how do we design a game with inherently variable living things to provide enough consistency in the gaming experience to make it enjoyable? Related to the second question, there's the more philosophical question of how necessary is consistency in the gaming experience? We know that some video games rely on random number generation, but they typically use it in very specific situations. But biological variability is pervasive, so does the randomness in biological systems detract from the gaming experience? And finally, a major question we also wanted to explore was, how can we create a mixed reality biotic game with this technology? And what does mixed reality even mean in a biotic game? So since we wanted to test microfluidic mazes in conjunction with light stimuli, we thought that Pac-Man would be a good base for our game. It has a recognizable maze, and the goal is to steer the Pac-Man character around in the maze. Both of those things have pretty straightforward analogs in real life. The microfluidic maze could be used to create the Pac-Man maze, and the LEDs could be used to steer the cells around. But what to do about the Pac dots, the pellets that Pac-Man collects for points? Since it was not within our technological capabilities to create real nutrient pellets for the Euglena to collect, we decided to create completely virtual Pac dots placed along the corridors of the microfluidic maze. How do we get real Euglena cells to interact with the virtual Pac dots? Well, because we use a webcam to view the cells, we can use computer vision to track the cells and remove the Pac dots as the cells move into them. At this point, we're already starting to merge a virtual world with the real biotic setup. But the virtual Pac dots don't have any real effect on the cells inside the setup, which is fine because in the original game, when Pac-Man runs into the Pac dots, they don't change his behavior in any way. This is not the case when he runs into a ghost. When Pac-Man runs into a ghost, he dies. The ghost has an effect on Pac-Man, and we thought it would be interesting to have a virtual object, such as a ghost, have a real effect on living cells. Of course, it would be cruel to kill or harm the Euglena if the cell were to run into a ghost that it can't even detect, so that was out of the question. But we do have the ability to confuse the Euglena and set it spinning in place by the projector. This would make it difficult for the player to steer them, which is like a temporary disablement of the cell. So for the ghost, we had a projector light up the pixels around the cell for 5 seconds, during which time the cell is difficult to control. And this, I think, is a true example of mixed reality. The virtual ghost is transformed into a real-world effect that changes the cell behavior and, in turn, the way that we play. So we're interacting with real cells through a mixed virtual and real interface. So that's what we started out with, a microfluidic maze for the Pac-Man maze, completely virtual Pac dots, and a mixed virtual real ghost that interacts with the cells through cell tracking and computer vision. The hardware all worked like we thought it would. We found that cells could be steered around in the maze if the corridor widths and height of the chamber were at least 100 microns in size. We also found that cells tended to get stuck in dead ends, so we tried to have as few dead ends as possible. Putting this all together, we started our iterative game design process. We went through 5 iterations, which resulted in the final game. I don't have time to go into all the details here, but I do want to highlight some important lessons that we got from the design process. First, to give a more consistent challenge, rather than track all of the cells that happened to be within the setup at the game start and give them all the ability to clear Pac dots and score points, we tracked a defined subset of cells depending on the game difficulty level, usually 1 or 10 cells. In the highest difficulty level of using a single cell, placing a virtual avatar over the tracked cell helped spectators quickly understand what the player was looking at and trying to get the cell to do, which greatly increased spectator enjoyment and appeal. We did find that players became frustrated when the cell with the avatar got stuck or seemed less responsive than other cells that were on the screen. To help mitigate their frustration, we implemented what we call a hyperjump routine, where players could choose to switch the avatar to another cell chosen at random. Test players actually had a lot of fun with this feature, and sometimes even used it to move to cells in different areas of the maze to be able to score more points. So these ended up being the possible game events in Pac-Euglena. On the left, you see the events triggered by the player. So steering by the LED stimuli was done with the W, A, S, and D keys. Pressing these keys reflected what the player was trying to get the Euglena to do. So if you wanted the Euglena to move down, for example, you'd press the S key, and the LED on the top side of the screen would light up. Note that because of response variability in the cells, some cells may not cooperate and move in different directions from what the player intends. The hyperjump is also triggered by the player by pressing the J key. On the right are all the events triggered by the Euglena cells via cell tracking. They collect Pac dots and fruits for points and can interact with the ghost. We took Pac-Euglena out for an informal user test at a university event. 18 players tried out this game, and it's important to note that all of these players were university students who had worked in bio-related labs before, so this isn't a representative sample of the general public by any means. But we thought it would be a good first test ground for this game. After they finished playing, we asked them to complete a short survey designed to figure out whether the game was at all playable, what we did well, and what could be improved. There were a lot of interesting things said during the user studies, but we'll only get to summarize some common themes here. First, the negatives. Many users found the control scheme unintuitive. Since we had the controls mapped to what the players wanted the cells to do rather than the stimulus that they were applying to the cells, and the cells weren't always cooperative, this did cause some player confusion. It may be more intuitive to map the controls to the stimulus instead, since that is what the user directly controls, but doing so may de-emphasize the variability inherent in biological systems. It's something to consider when designing a biotic game. Another common suggestion from users was to increase the magnification so they could see the cells more clearly. This brings up an interesting point about choosing scaling in biotic setups. Because we're working with real organisms, we have to work with both their natural size and timescale. We want to choose a magnification where the cell responses are noticeable to people. This depends on the speed of the organism. If you're too zoomed in, the cell appears to be moving too quickly for you to interact with, but if you're too zoomed out, the cell is both hard to see and may not appear to be moving at all. Our magnification choice did have other constraints. We did not have a moving stage, so the entire microfluidic maze needed to fit within the field of view. And since we also wanted the maze to be recognizable as the Pac-Man maze, it had to be relatively large in order to let the Euglena move around more freely. In future games, we would probably choose to either use a simpler and smaller maze with fewer corridors, or implement a moving stage to follow the cells around. On the positive side, almost every player reported learning that Euglena are light responsive. One player mentioned that they learned that computer vision was difficult, which is cool because it shows that this player noticed other parts of the technology needed to create this game. Users also reported really enjoying the fact that the game used real, living cells. For a lot of players, it seemed to be the most striking aspect of this game, mentioned by over half of the players as something they found entertaining or engaging. One player said, for example, that being able to control the Euglena was very exciting, and another said that they enjoyed working with live organisms. Finally, many players did find that the variability made the game more challenging, but interestingly, some players reported actually enjoying that aspect, saying, for example, that they were amused by how the Euglena didn't really do what they wanted it to do, and also that they liked that they, in their words, could engage with a living thing that they communicated with but could not fully control. In conclusion, we created a mixed reality biotic game where players can steer living cells around to interact with virtual objects. The ghost interaction is particularly interesting because when the Euglena cell runs into a virtual ghost, or when the ghost runs into the Euglena cell, as you see here, it is transformed into a real stimulus which temporarily disables the cell, giving us an example of a mixed virtual real object. In developing this game, we demonstrated that it is possible to steer Euglena cells through complex microfluidic mazes with a minimum feature size of 100 microns, that you can deal with biological variability by using larger subsets of cells or giving players the option to switch between different cells. But we also found that biological variability can, in some cases, even increase player engagement and amusement. This is a cool thing to know because variability in living systems can never really be completely eliminated. But maybe that unpredictability is what makes biotic gaming enjoyable, and is what actually makes us appreciate that we're interacting with real, living things. We hope you enjoyed our presentation, and thank you for your attention and interest.